So in this video we're going to do a quick benchmark, and we are going to benchmark how long does it take to find an element in a key value store with two different implementations. One is a simple vector, so we have in our vector the key and the value. So like this, we have a key which is response to value, and in another one is a standard HashMap. So in the vector, what we do, we just scan the whole vector, compare the key. So like here, we compare the key with the one we want, and if it is, we return the value. And I already wrote the part for the vector, which is quite simple, with this part over here, and I already plugged it inside criterion, which is a very standardish framework for benchmarking Rust. And eventually we bench our input over this set of parameters, so a size and its ratio. The size is how many elements are actually in the collection, so it will be 128, 64, 32, 16, 8, and 4. And then the hit ratio is how many of the key we are going to look for are actually inside the container. So what I'm interested in is mostly high hit ratio and size that are in the order mostly around 16 for like very small size. This is because it's going each one of these, so it will be a thread in a concurrent program, concurrent software, and I believe it will be quite rare. There will be people around 128 threads, because do we need 128 or at least 64 core in the computer, and I mean, they start to be a lot. Yeah. So first of all, let's see the output of this one, which criterion, if you do cargo run, will compile and give you this extremely nice output. So I'll give you what it's doing. So benchmarking simple vector, where simple vector is this string over here. Bench input is the name of the function. Bench input is the input. Is the input that we define. So if you see, the first one is size 128, hit ratio 0.9, repetition 1000. So we see bench input, size, hit ratio, repetition, so on and so forth. And what criterion does is run that for 3 seconds, and then it tries to give you something that is significant, trying to respect your time. So first of all, it must be significant, so at least a lot of iteration, and then try to respect the time that you give. In this case, I give 5 seconds, and we see that the latest one will be in the order of 5 seconds. The smallest one, size 4, will be in the order of 5 seconds, doing a lot more repetition than the bigger one. And after all, we give you it's run the benchmark and then analyze the result, and then it print you something interesting. So the time, I believe, is the different percentile. What we are mostly interested in is a general idea. I mean, they are very, very similar: 5 seconds, 5 milliseconds, 5 milliseconds, 5 milliseconds, and if you have the input, you go 2.5, roughly 2.5, roughly 2.5, roughly 2.5, which is pretty much what we expect. Also interesting, the hit ratio. So 0.9 is going to be faster than 0.1, which is, I mean, if 90% of the elements are actually in the collection, for a vector it's going to be faster, because I find the element. I mostly find the element, so I mostly find the element around 50% of the collection. While if only 10% of the elements are in the collection, you're going to scan the whole collection like 90% of the time. Like if 0.9 element are in the connection, you're going to scan half of the connection in general, plus a little bit for the elements that are not really in the collection. So this is the general idea. This is another sample, the run. You can see a little bit of difference. Now I'm running the recorder, so it's a little slower. But what is interesting about criterion, they give you also give you a confidence interval and let you know if this is really something significant. So 7% is significant because it's quite big generally, and the p-value is greater than 0.05, is smaller than 0.05. So it tells you performance has regressed. Let's go to code the benchmark for the HashMap. So it'll be quite simple. And we do have a function bench HashMap that takes this B, which is an internal structure of criterion, and then takes our input, which is this bench input over here. Oh, also interesting is that I need to define the debug method. This, I believe, is used mostly here. So if I define the debug method, you know what to print. So you can print this nice stuff over here. I believe this is the only reason, the most important reason why we need to define the debug method. Let's go back over here. So bench a vector, bench an HashMap, bench input. Okay. So this must be a reference of bench input. We're setting the same signature, and eventually here we need to do this bencher.iter, and then we pass a function that keeps running. So over here we could just bench function with input simple HashMap simple vector bench HashMap and the argument. So argument are this one, this is just a vector input. Bench HashMap is the function, and this is the simple name that we got. Eventually, this is going to take all over input, so each one of these will run inside bench HashMap. Bench HashMap, the bencher will just run this part over here, so we run the setup once, and then we run the bench iter several times. So what we need to set up our test. How we do it? So in general, it's a good idea to have something random, and then let's get over and get a new HashMap. So how do HashMap works? We should have them over here. We need to import, and then it's quite simple. HashMap.new. So I can put the HashMap over here, and then down here a container HashMap.new. Let's see if you did anything bad. Better expression found. Let's see. Oh, 1 and 4. What is the problem here? Is that this one? I'm gonna be wrong. Good. Cannot infer type for K. We don't care. Eventually we'll be able to do it when we use the container. Because we pass in the value, so it will be able to infer the correct type. This idea. So we can just repeat what we were doing before. So input size container dot is an insert random string and random number. It is enough. Let's see. Just not implement a copy trait. So this is a different error. Say that we move the value, then just clone it. We don't care in this case. So just args dot clone should be enough. Let's see. No, it's not. No missing a clone for bench input. So derive the bug and clone. Good. So it doesn't know how to clone a vector, but it doesn't know how to clone a bench input. You can just copy stuff around. It'll be fine. So let's go back here. So what we did is to insert a random string and a random number inside the container. And then at this point, we should repeat this procedure. What's happening here? We have a vector with a capacity of number of repetition. And inside this vector, we throw a coin, and if this random number we get is less than the eta ratio, this number is less than the eta ratio, we go here. So we get another random number, and we put the result, and we put the value of that random number inside this target. Otherwise, we put the key, not the value, the key, because 0 is the key of the random value inside the target. Otherwise, we put something randomly, not random stuff. In our case, this is a little more convoluted, I believe, because I need to get a random key, which is not simple. So what we can do actually is to just push the key that we generate here. We just push in another buffer, which is just another vec, not a new vec. Container.insert was also buffer.push random string, and this will likely complain because random string will be taken here and then here. Let's see. So, semicolon missing. Okay. Let's see. Exactly. So another move error, because this string, random string, is owned by the container now. But I try to push into the buffer. And simple stuff to do, also in this case, is to clone it. We can discuss different strategies, but in this case, clone is the most appropriate, I believe. Nice. Finally, let's go back into this part of the code and let's do something similar. So we have a target. We generate, this is an empty target. We generate, and we have an empty targets, set of target. And for each repetition, we generate a random number. And if it's less than each ratio, we generate an index between 0 and buffer, and then buffer.index without 0 this time get cloned and add to the targets. Let's see if this makes sense also for the borrow checker. Yes, it does. And now, last step. So for target in, can have a reference here, targets. So for each of this one, which is that some are in the containers, some other are not, but for each of that one, we try to get it. So container dot target. That's pretty much it. Now I'm afraid that it will. I'm afraid this will just be compiled away because we don't use this result value. Also here we don't use it, but there is a loop, so I know that it's going to be faster. I know by the timing that it's actually doing the work. In this case, I'm not sure. What we can do is to try. Let's be a little smart because this takes a little bit of time. So let's just try a new one. No entry found for key. So it's trying to do it and it's planning. Very well. No entry found for key. So get return a reference referring to the key. Let's have a simple get, because usually implement. It does usually implement the. Where I can see the int API, random stuff, entry. Let's have a simple get. Container dot get target, and this should return us an option, so it does not crash. Let's see if it's true. It's running, which is good. We can already see. So in theory, the size should not matter. It should be roughly the same speed in all cases. It almost seems to be the case. And just to make sure, let's go back to criterion. Criterion black bots. So what is black bots and criterion? Is a function. A function is a part of the optimizer. It's to prevent the compiler from optimizing any computational benchmark. But make our some performance error fail to prevent code from being eliminated. Let's just use it and see if the performance change. Dot black bots over here. So we already got enough information that we can definitely kill it. Let's see if the black box makes any difference. No, pretty much the same. What can I say? Because it's 5 seconds for 10k iteration, which is roughly similar to what was above. But let's wait. Is 500 nanoseconds. So now we get our information that we want. We can run them together. So we run both the vector benchmark and the HashMap vector. Let's compile, no error, and yep, let's wait. I will cut this part of the video. Eventually, let's go back into the code and see if there is something interesting we can explain. So, bench vector, I believe it's quite interesting how we avoid the borrow checker errors. So first of all, let's repeat what is our input. Input is what we are benchmarking. Batch input, we have a size of the container, so how many elements we want to have in this container. The hit ratio, so how many times element that we look for is actually in the containers, and repetition, so how many repetition we do, how many search we do, because just once is just too fast to be actually benchmarked. So if you go to the bench vector random thread random number generator, we create our container, and we start to push to create a random string, a random number. We push it. Here you see I don't clone it. This is because the ownership just belong to the container. So eventually I create this string, allocate this memory somewhere, and say, okay, container, now you have this memory now belongs to you. So you know how to do it, what to do it with it. It's not a problem for random number because it's a type such that is so small that is influent how this is used. Then the problem starts with the targets. So the targets is just a list, actually a vector, that contains all the elements we want to look for. So, as I say, I throw this coin and eventually I get the element. This element now must be cloned because it belongs to the container. So what is happening here is just some mem copy. So I'm taking the element, I'm making a copy in a different part of the memory, and that I'm pushing that into this other vector. In this way, both of them have their own targets, and whenever container will go out of scope, we delete its own part, while targets will delete its own. Can I do differently? Can I do with a reference? In this simple case, without the else, yes, I can. So I can just create a reference here and remove the clone. However, then the type of strings, so like normal strings, or reference to strings, which will be different from what we get from here. So there will be this mismatch between what I get above, which is a reference to a string, and what is below, which is a string. And it will be complex for the container to know what to do. In this case, so it's just simple to clone the memory. Also, I can do it. I could do it because first I allocate the container and then I allocate the target. So when we finish everything, when both target and containers goes out of scope, so roughly here, the first one to be deallocated will be target, and then will be container. So target will be deallocated. We forget all the reference to the stuff in the container. Then container will be deallocated, destroying all the string. But two pointers won't point anymore to anything because two pointers inside target are already being eliminated, so it'll be fine. And that's pretty much what we are doing. Let's see back. Benchmark, nice, finish. Hopefully didn't get too bored. So we have all this nice information. And I see that for an input size which is big, 128, a vector take 5 milliseconds. 5.5 milliseconds. And it takes while a HashMap for the same input take 10 times less, 500 nanoseconds. However, the HashMap keep the same performance over and over again, so it does not matter how big is the container, seems like it does not matter. It just roughly always 500 nanosecond. While our vector, our simple vector, in this case is faster. So when it's very, very small, like size 4, this is faster. Size 8 is comparable, slightly faster and comparable. Size 16, okay, there starts to be a big difference. So already in 16, the HashMap is much faster. This one last thing to try if we have time. How much time we got? No, that's already too long. Yep, so that's pretty much all for us. You can try to see HashMap with, we need a custom crate. No. So the standard implementation of HashMap using the default is not the fastest you can get. But we have a different crate, FNV, which is usually faster for some cases. And we already showed that the HashMap is much faster in the case we care, most cases at least. So it's not necessary to go up to FNV. And that's pretty much all for the video. Thanks.